Vectors are very widely used for describing the motion in space, the motion of a particle in space. So let's take a look at the idea of velocity and acceleration. Now we discussed prior to this the ideas of the tangent and the normal vectors along with the curvature of a space curve. Now we're going to take a look at how these elements are used in physics to study the motion of an object, including velocity and acceleration as the particle moves along a space curve. Now suppose we have a particle that moves along a space curve such that the position vector at time t is given by r of t. So I'm going to do this in R2 because obviously it's more difficult to draw in R3. So I have some particle moving along, say, this curve. And at time t, the particle is right here. So here's my position vector, r of t. Now, at time t plus h, this is where the particle is. So here's my position vector, r of t plus h. Now, my actual direction of travel at time t can be described by the tangential vector t. However, for small values of h, the vector r of t plus h minus r of t over h, which I'm sure you recognize that format, will very nicely approximate the direction of travel. In other words, this vector will very nicely approximate the tangent vector. The magnitude of r of t will then measure the size of the displacement and that's the size of displacement be measured per unit time. Per unit time t. Based on this definition, we can start taking a look at the idea of the velocity vector. Say velocity is then going to be the instantaneous amount of displacement, or it's going to be the limit as h goes to 0 of r of t plus h minus r of t over h, which we will write as r prime of t. Therefore, the velocity vector is actually the tangent vector and points in the direction of the tangent line. Now, keeping in mind here that there's a difference between the tangent vector and the tangent line. The tangent line at this point, r of t, will be a line that takes off like this, but the vector, and I put in the unit tangent vector, would be simply a vector at this point. Now, recall back from Calc 1, if s of t was a position function, then the rate of change in position, s prime of t, that equals velocity, which we commonly denoted as simply v of t. It's the exact same concept here when we're dealing with vectors, only rather than s of t, I'm using the position vector r of t. Now, the speed of a particle is then the magnitude of the velocity vector. So speed is actually simply the magnitude of the velocity vector, v of t, which is the same as saying it's the magnitude of r prime of t, keeping in mind again that these are both vectors, which we can also think of as ds dt, where s is the arc length, or our position. So we can actually think of this as being, the rate of change of distance with respect to time. With one-dimensional motion, acceleration a of t equals v prime of t, the first derivative of the velocity, which equals r double prime of t, the second derivative of the position vector. So if I make all these vectors, these are all three different expressions that say the exact same thing. So let's go ahead and work out a quick example here. Suppose we have a position vector given as r of t, and again as a reminder, these are all vectors, equals t 2 cosine t sine t. Now find the velocity and acceleration of a particle moving along the space curve that's been defined by this vector r of t. So velocity is r prime of t, which equals, let's take the first derivative of this position vector. That's going to be 1 negative 2 sine t cosine of t. Acceleration, again as a reminder, these are in fact all vectors, will be the same as v prime, which is of course the same as r double prime of t, which is going to give me 0, negative 2 cosine t, negative sine t. Now, based on the velocity vector, I can now say speed. Remember, speed is simply the magnitude of the velocity. It doesn't have direction. That's the difference between velocity and speed, is that velocity is a vector. It has both magnitude and direction. Speed has magnitude only. So speed is actually equal to the magnitude of the velocity vector, which equals the square root of 1 squared, which is 1, plus negative 2 sine t plus cosine squared t. So this is simply going to be the square root of 4 sine squared t plus cosine squared t plus 1. So the speed is still a function of t here, so until I give it an actual value of t, I won't be able to define exactly what the speed is. It's a function of t, so clearly the speed is changing as this particle is moving along because, well, the velocity is changing.